So last time we started talking about heuristics, approximations, ways to solve problems in a way that's quick and dirty, good solution, fast, hopefully provably good. And we said there's lots of ways to do that, to come up with heuristics. The idea is to get into local minima and hopefully global minima, and not get trapped in local minima necessarily, even though global optima are hard to find. Greedy descent will get you into local minimum. There's various slower approaches, branch and bound, linear programming, kind of integer linear programming approximations. There's also kind of wishful thinking algorithms like simulated annealing and genetic algorithms, but those are last resort kind of algorithms. That's when nothing else works. You can throw stuff at it. We gave a heuristic for minimum vertex cover that's no worse than twice optimal. And the idea was you can pick nodes in pairs across random edges, throw both of those into the solution. The optimal solution must contain at least one of these two nodes for vertex cover to even be a solution, never mind optimal solution. So you never worse than twice optimal. And that's a linear time algorithm. That's the best we know so far, even though this particular heuristic is over 40 years old, 45 years old. Maximum cuts, similar idea. You keep throwing nodes across the cut, and you do it in a way that improves the cut size, that is, increases the cut size. If you keep doing that, eventually when it peters out and can't improve the solution anymore, the solution thus obtained is no worse than twice the optimal, or at least half the optimal. Here we're trying to increase the cut size, not decrease the vertex cover size. So this heuristic is pretty good. The problem has a lower bound on its approximability, and this is twice optimal. And it's easy to show it's twice optimal because the optimal solution will have at most all the vertices on the two sides such that all the edges cross the cut. And this solution here will have, for each node, most of its edges, outgoing edges, most of its neighbors being on the opposite side of the cut. So at least half the vertices will cross the cut. So it's at least half as good as the optimal. And of course, we talked about various ways to optimize it even further. Here you can pick pairs to swap, or do it in different random orders, and then take the best of n solutions. But all of these will inherit the two opt. You can do it in parallel as a meta-heuristic, take the best of the n solutions, and it'll inherit the 2 times opt upper bound, and potentially be a lot better than that, even by taking the minimum, in this case the maximum, because we're maximizing the cut size, maximum of all the solutions, and so it's the best of both worlds. I think we stopped with traveling salesman, is that right? Did we? Yeah. So traveling salesman, we're going to present now a 2-opt solution approximation heuristic for traveling salesman. So this works when when a triangle inequality holds. So traveling salesman against NP-complete. Not only that, TSP in graphs cannot be approximated to any constant factor. We know that. Unless p is equal to np, of course. So it can be approximated to any constant factor in polynomial time. But here's a 2 times optimal approximation if the triangle inequality holds. Okay, so first, we take the points and we compute a minimum spanning tree over those points. That's easy to do. That's prim or Kruskal, any kind of minimum spanning tree algorithm. And then we traverse it in a depth-first manner, starting at some root, doesn't matter which. So the green tour here shown animated is the traversal of the minimum spanning tree in blue. And that traverses its spanning tree all the way around, all the way back to the beginning. So the green is twice as long as the blue, right? Because every edge in blue, every minimum spanning tree edge in blue is traversed twice by the green, once on the way down and once on the way up in this depth-first tree traversal. So the green is a tour, but it's not a minimum traveling salesman tour. In fact, it's not a traveling salesman tour at all. because some vertices here are visited by the green tour more than once. Right? For example, this vertex here is visited once, twice, 3 times, 4 times, as many times as its degree, actually. So it's not quite a traveling salesman tour. So we convert it into a traveling salesman tour by insisting on visiting everything exactly once. So the red tour here shortcuts or short circuits the green tour by skipping all the ones that were already visited. So this is new, but then this was visited, so it goes to the next unvisited node in the green tour for its next node. So the red basically follows the green, except sometimes it short circuits and bypasses some green tour nodes because it's already been visited before, those nodes. So the red tour is the one that we output, and that's our heuristic solution. Let me understand this heuristic. That's what it is. Now, the question is, the big question is how good is this red tour compared to the optimal? And we're about to prove it's no worse than twice. Okay, so we call the red tour the shortcut tour, color-coded red. So clearly, the blue and the green have a factor of 2 relation between them, right? The green is twice the length of the blue, because every blue edge appears in the green twice in a green tour, right? Separately from that, the red tour is less than the green tour. Why is the red tour less than the green tour? Because of the triangle inequality, right? Every time you bypass a node, so the red, instead of going here, it goes directly to there. Well, there's a triangle here, and from here to here is shorter than from here to here via this third intermediate point, right? So for every triangle, one of the sides is smaller than the sum of the other two combined, simply because the smallest distance, the shortest distance between 2 points is a straight line, not a line going through some third point. Right? So the red is not bigger than the green. So I'm denoting this relationship here. That's true because of the triangle inequality, right? The metricity of the underlying metric. So for distances in the plane, that's true. For distances in 3 space, that's true also. In fact, it's true in other metric besides Euclidean metric. It's true for Manhattan metric, for Chebyshev metric. That's what they call metrics, in fact, because the triangle inequality holds. How many get this relationship? The red is not as, okay, good. Now, we already said that the minimum spanning tree and the green tour is exactly twice the MST. Okay, so I'm not going to say that here yet, but let's look at the next one that's less obvious. The minimum spanning tree cost in blue is less than the optimal traveling salesman tour. Why is that true? Why is the minimum spanning tree cost in blue less than whatever the optimal traveling salesman tour is? Which we have no idea what it is because it's NP-complete to compute, and we can't compute it in polynomial time as far as we know. And so we may never know what a particular TSP tour is for a given large point set. But for sure, we can always be rest assured that the minimum spanning tree cost is less than the optimal traveling salesman tour. Why is that true? Anybody can think of a proof or a reason? Yeah.
There's one edge difference, like if you take an edge of the TSP.
Yeah. So if you take a tour and you remove one edge, which edge, I don't care, just remove one edge, what kind of an object do you get? A tree. Not necessarily the minimum spanning tree, but a tree. Well, on this side of the inequality, there's the minimum spanning tree, the best possible tree. Here, there's just a tree by removing an edge from a tour. So the best tree will be at least as good as any arbitrary tree obtained by removing an edge from a tour. How many get this? Okay, good enough. So now we put it together, and we multiply both of these sides of the inequality by 2, because if something is less than something, then multiply both sides by 2, and twice that first thing is less than twice that second thing yet again. So that's why I multiply it by 2. But the reason I multiply by 2 also is I want to say that the green tour is equal to twice the blue MST tour, like I mentioned before. Right? So now we have the complete set of inequalities and an equation in the middle. So the red is less than or equal to the green because it shortcuts and short circuits the green by the triangle inequality. Then we have the green is equal to twice the blue, and twice the blue is less than or equal to twice the minimum traveling salesman tour, because take the tour, remove an edge, and you get a tree, not necessarily the best tree. Bottom line is, you get end to end, the shortcut tour in red is less than twice the optimal TSP, and that's the end of the proof. So the red tour will never be worse than twice the best possible traveling salesman tour, whatever that may be. How many understand that proof? Okay. Any questions about that? So we gave a heuristic for TSP. It's pretty simple heuristic, but it has this mathematical guarantee that it's never worse than twice the best possible. Okay. By the way, try not to shake that table too much because the camera is on it, and last time we had a lot of jitter on the pictures, so be careful. Thank you. So, any questions about this? So let me ask you questions. How fast is this heuristic? How long does it take to run for endpoints? Endpoints in the Euclidean plane. That's pretty straightforward, right? How much? Linear? Not quite linear, it's close. If this was linear time, you could do the MST in linear time, right? But you can't do an MST in linear time as far as we know. So what else? But it's a close. That answer is almost there. What's the bottleneck in this computation here? Where's most of the time expended here? Is it traversing the MST in a depth-first search? How long does that take? Linear, right? Is it then going on the green tour and bypassing it, giving the red tour? That's kind of linear too, right? You can do it in linear time. The bottleneck is the minimum spanning tree routine, right? That's where it's the only non-linear, non-obviously linear. That's n log n for the Euclidean plane. You can show n log n lower bound for Euclidean minimum spanning tree. So it's roughly n log n asymptotically, not roughly, but is n log n exactly asymptotically. So it's pretty fast. And this was known for a long time. This was known since probably the late 60s or early 70s. And there's a way to compute traveling salesman tours heuristically that are no worse than 1.5 times the optimal. And that's a algorithm by Christophides. I don't have a slide on that, but let me show you how it works. So you have you do a minimum spanning tree, and then you look at all nodes of odd degree. So this is odd degree, that's odd degree, that's odd degree, that's odd degree, and these two are odd degree. And it could be other nodes of odd degree, but for this particular graph, 1, 2, 3, 4, 5, 6. And then what you do is you do a minimum matching on all the nodes of odd degree. So minimum matching is you connect nodes pairwise to minimize the total edge distance. Okay. So this might connect to here, and this might connect to here, and this might connect to here. By the way, in a graph, what can you tell me about the number of nodes of odd degree? The parity of the number of nodes of odd degree. Is it even or odd? It's even. Why? Why multiplies the number of nodes of odd degree in any graph, that number must be an even number, can't be an odd number.
The total number of nodes equals to twice that edge.
Yeah, the total sum of degrees is twice the number of edges. How many get that? It's so because every edge adds 2 to the total sum of degrees. It's called the handshaking lemma, by the way. Handshaking because if you have a party and people shook hands throughout the evening, you don't know who shook hands with who, but a number of people shook hands with each other. The total number of handshakes, if everybody reports how many times they shook hands, and you add up all those numbers, the total number of handshakes experienced by people is an even number. Because every time somebody shakes hands with somebody else, that count goes up by 2, because each one shook a hand just now. You can't shake hands with yourself. And even if you could, that's still 2, right? This hand shakes and this hand shakes, that's 2 handshakes, even though you're doing it yourself. So that's called the handshaking lemma. So there's only an even number of nodes of odd degree, not an odd number. And so you can connect them in pairs. There's nobody left over. And once you do that, all the degrees become even. When you add all the edges that are the minimum matching, are, on nodes of odd degree, you make all the degrees of the odd degree nodes, you make them even. How many understand that? Okay. And if you have a graph with the degrees all being even, there's an Euler tour on this graph. How many get that? Euler tour picks up all the edges, not all the nodes. Well, it picks up all the nodes also, but it also covers all the edges. An Euler tour traverses every edge exactly once. So once you do an Euler tour on this, that's your output. Of course, you also want to bypass the Euler tour to remove duplicates, because the Euler tour on this will have some duplicates. So an Euler tour on this might be, let's just draw it. Start here and go here, and then go here, and then go here. And instead of going back here, I'm going to go to the next one, next unvisited one, just like this strategy here. And then go here, and then go here, here. Instead of going here, because I visited this already, I'm going to go straight here. And that's my TSP tour. So the TSP tour bypasses the Euler tour. I didn't bother to draw the Euler tour, it would just be too cluttered. So the TSP tour here in green consists of the MST in blue plus all the minimum matching edges in black. So the green can't be more than the blue plus the black. And the blue plus the black is the MST in blue, which is 1 MST cost, not 2. And then the minimum matching. Make the matching minimum total length. And here's a trick. If you have a tour, if you have some tour, let me draw a few nodes, the minimum matching is no worse than half the tour length. Why? Because you can take every other edge. You can take all of these edges. That's one candidate for minimum matching. Or you can take all the other edges. That's another candidate for minimum matching. Here, here, here. You can take either the even or the odd edges. And together, the green edges plus the black edges equal the blue edges. But the blue edges is the minimum traveling salesman tour. So at least the green or the black edges, one of them is less than half of the blue tour. Because if both were bigger than half together, they'll be bigger than the whole because they're disjoint. So a tour implicitly contains 2 minimum matchings, one of which has to be equal or less than half the tour. How many get that? Okay. Any questions about that? Yeah.
Usually the approximate TSPs sacrifice like the weight, like the shortest distance do any approximate TSP algorithms give up like touching every point?
You could, but then it's just a smaller tour of the smaller subset of points. But you could do that. There's literally dozens and dozens of variations, right? I mean, I came up with one back in the day where the points are moving, right? Moving target TSP. So the points can move, and now you're chasing moving points, which is even harder than this case where the points are all stationary, they're fixed. So this is a special case of mine where here the velocities are all zero. But you can assign vectors to them and start, and there's lots of other variations. There's lots and lots of variations. There's even ones where you visit some points more than once, not just 0 times like you said, but 2 or 3 or 4 times. You can put a bound, both upper and lower bounds on how many times you're allowed to visit points. Okay, but the green comes from the MST plus a minimum matching, but we just said the minimum matching is half the tour size. The TSP is less than the tour size, or close to it, potentially. So the total tour in green is no worse than the MST plus a minimum matching, which is 1 plus a half times the optimal minimum traveling salesman tour. So this heuristic here is no worse than 1.5 times optimal. So I just gave you a 1.5 times optimal heuristic for TSP. As long as the triangle inequality holds again, because when you bypass nodes, you can't take longer, you must only take shorter. It means the triangle inequality has to be in effect for this to work. Yeah? No, the MST is not unique necessarily, right? Okay, so he's asking about uniqueness of MST. So give me an example where it's highly non-unique, when there's literally an exponential number of minimum spanning trees all having the same length.
A connected graph with edge weights 1?
Yeah, the complete graph with all the edge weights being 1. Any tree is a minimum spanning tree. They're all the same weight, right? Or a grid graph, where all the grids, like all these points, any mesh, any tree will be the same weight as any other tree. The interpoint distances are all 1 between any node and its neighbors, right? So if you want to connect points in a mesh, there's lots and lots and lots of different trees, right? Right? One tree will look like this, another tree will look like this, another tree will look like this, another tree will look like this, and so they're all equal weight. These are all unit distances in this mesh. So not only it's not unique, it can be exponential number of trees. In fact, every tree can have the same weight as every other tree in the case of connected graph, fully connected graph on n nodes with all the weights being 1. So when you say the best MST, depends what you mean. There's various ways to define it. You can say a minimum spanning tree with a minimum maximum degree, with the smallest maximum degree, say. So for example, this tree here has degree 3 here. This one has degree 2 at most everywhere. But that's not necessarily the best. You can say the minimum spanning tree having the shortest maximum path between any 2 nodes in the tree. In other words, shortest diameter. So this tree is not so good because the distance from here to here in the tree is huge. Here the distance is pretty short, right? So if this was a clock tree on a circuit, you don't want this. You want something more like that, right? In other words, you don't want a tree that spans all the nodes like this. You want a tree that spans all the nodes like that. Because here the distances between nodes in the tree are not that great. Here it's huge distance from one node to the opposite node. So you can start putting other constraints and other considerations. Things can get quite complicated, actually. Yeah, I wrote some papers on it back in the day, and it's an interesting problem. Among all the minimum spanning trees, which one should you prefer, assuming there's a lot of ties? But for this heuristic, and even for that heuristic, it doesn't matter. any minimum spanning tree will do the trick, and you still get your bound. You don't have to optimize it much more than that. Yeah.
If we're allowed the edges with negative degree or a negative weight, does that mean that TSP has to just say no, there's no shortest tor?
Well, if the edges have
If there's like a cycle.
negative weights, it's still well defined because the negative weights will just keep the weight, the total, tour weight lower if you pick that edge. So it's still well defined actually. So you don't have to say no. You can just say, okay, if there's a very cheap edge, by cheap I mean now negative weight, fine, take it.
You're not allowed to touch points twice anyway, so.
Yeah, that's right. So it's still a permutation. So all a TSP tour is a permutation of the nodes.
Yeah.
You can think about it as just a pure permutation of the nodes. So there is some permutation that will minimize the total tour length regardless of what the edge weights are, positive or negative. And you can have plenty of negative cycles. Still, there is some permutation that has the least weight. And the total weight can go into negative territory itself. The weight can be minus 17. But then if that's the optimal, you won't be able to get a weight of minus 18 or minus 20. And then that's, if you want to define that as your optimal, that's great. Then that's what you get.
Exactly one's requirement, then would you end up with a bad situation?
Yeah. So if you can have variations of this problem that have no best answer, because you can keep going around negative cycles, winning and winning and winning, and there's no optimal tour if you're allowed to visit nodes more than once without any bound. But if you're allowed to visit nodes, say, at most 5 times, again, there's an answer, even if there's negative weights or even if there's negative cycles. If you're allowed to visit any node at most 5 times, well, there's some way to visit all the nodes at most 5 times. It'll get you the best cost. And now you're back again to an optimal solution somewhere. Any other questions or thoughts about this? So we showed a 2 times optimal. We showed a more complicated 1.5 times optimal. And this is from the late 60s. This algorithm was from 1975. It's 76 maybe by a guy called Christophides. And for almost 20 years after that, nobody knew if there exists a better than 3/2 optimal solution to Euclidean or metric TSP. And in 1996 or so, Arora showed that those solutions are arbitrarily close to optimal. But how fast is this algorithm, by the way? Where's the bottleneck in speed here? What would you guess? MST, but we also need a minimum matching. Why can't we take any matching? Because remember, we need a matching that's no worse than half of the optimal traveling salesman tour. So we can't take any old matching. It needs to be the best possible matching. That's guaranteed to be no worse than half of the optimal TSP tour. So we need a minimum matching, and that's actually not easy. You can do it in polynomial time. It takes roughly cubic time, or n to the 2.5 roughly, actually.
Is that for bipartite graphs?
It's for arbitrary graphs. I think you do n to the 2.5 for arbitrary graphs. For bipartite graphs, you probably do it faster than that. But either way, it's not trivial. Doing minimum matchings is not easy. It's a lot more complicated than prim or Kruskal for minimum spanning trees. But it is polynomial time. So this heuristic here will get you, for about the price of n to the 2.5, it will get you 1.5 times optimal guaranteed solution. So you see, if you want a better bound, you pay more in time. They're still both polynomial, just a higher polynomial for the better bound. Now, if you run this in practice, notice something interesting happening here. Right here, the red path crosses itself. What does that tell you? Flip it. But if it crosses itself, it can't be optimal, right? Why can't a self-intersecting tour possibly be the optimal tour? It cannot, but why not? Yeah, you can always find a shorter tour if this happens. So if you have a tour, that crosses itself, never mind what happens here and here. So here's the rest of the tour, here's the rest of that tour, but here are the two crossing edges. Right there. What you can do is replace those two edges with two other edges, this one, and this new tour minus these edges, but plus these two other edges will be shorter than the original tour was, the self-intersecting tour. Why? Two words, triangle inequality. Because this triangle here, this distance is shorter than these two distances. And here, this distance is shorter than these two distances. So together, these two distances are shorter than these two green edges, which are the sum of these blue distances here. So triangle inequality, or metricity more generally, when you have a metric space, the tour cannot self-intersect. That's true in Euclidean, Manhattan distance, Chebyshev distance, 2 dimensions, 3 dimensions, any higher dimension than that. So whenever you see a self-intersection, you can do a flip like this. It's called a two-opt. Pick two edges and flip them like this. And the tour length will keep decreasing. And you can do this until there's no more ways to keep decreasing it. So you can do post-processing. What other heuristic modifications can you do? By the way, if you keep flipping it like that, will the bound still be okay? In other words, will the resulting tour still be no worse than twice optimal, or are you going to lose your bound all of a sudden? What do you say? How would you say you keep your bound? Yeah, because you're not worse off than you were before, and possibly better, so the bound's not going to degrade, it only improve, and all we're doing is keeping the old bound. We're not claiming any better bound. We're just saying the answer could just be better in practice. Yeah.
Checking every pair of vertices for intersections for every pair of edges, I guess, would that be like E squared?
Yeah, it'd be like E squared, but you can take some shortcuts because you don't have to compare every pair. You can take all the edges and then do line segment intersection test from computational geometry from last semester. Remember that? Or talked about it a little bit. So you can do it in n log n time, but here n is e, so you can do it in e log e time, not e time, not e squared time. And of course, you need to do it several times to keep finding intersections. So, but eventually it peters out. You can prove that after a polynomial number of times, this will peter out and stabilize, and there'll be no more improvements to be had. What other optimizations can you do here to try to get better answers? Take some wild guesses. There's dozens and dozens of possibilities, right? Hundreds maybe even. There's entire books on TSP heuristics, where they give you hundreds of different heuristics. This is just one of them. Doing two opt after the fact is another. What else? What about three opt? Finding 3 points that permuting them or changing them will get you a better solution. How many can imagine, not necessarily prove, but imagine that doing a 3 opt can find stuff that 2 opt can't in terms of improvements? Nobody? Three edges, let's say. So instead of uncrossing one pair, remove not 2 edges and then replace them with 2. Remove 3 edges. Which ones? I don't care. Some random set of 3 edges, such that replacing them with 3 new edges improves the tour in a way that can't happen with 2. How many can imagine, I'm not asking for a proof, can imagine that this is true? Okay, then I'll just tell you it is true. I mean, if you can't imagine, all right, then. Because I tell you what, let me give you some way of imagining that this is true. What if I increase that number k from 3 opt to 4 opt to 5 opt? What if I change it to n opt? If I take away n edges and replace it with n new edges, Could you see that that could improve it? How many see this will give you an optimal solution? You can find it will. If you remove all the edges and put them new edges in the best possible way, that is the optimal TSP tour. So as you keep increasing this parameter, k opt for k, from 2 to 3 to 5 to n, eventually you get the optimal tour. And before you even get there, you'll get just much better tours with larger parameters. Okay. Other things to try. We started a tour here and went this way. If you start the tour, say here, and start, you'll get a different red tour potentially. How many can see that? Yeah. So start here, find the red tour. Start here, find another red tour. Start here, find another. Find n different red tours. And what do you do with those n red tours? Take the shortest one. And then apply 2-opt to it, maybe on top of that. Are you going to inherit the bound? How many say yes? Yeah, of course, because this bound holds no matter where you started the tour, the red tour or the green tour or whatever. Right? It still holds. In fact, apply 2-opt to all of them, and then take the best of all the tours with 2-opt applied to each. Do you see that that could be better than finding the best tour and applying 2-opt to it? How many can see that? Yeah, now you're getting it. Because almost anything can happen when you apply optimizations, right? These kind of post-processing kind of steps. In other words, what we're saying now is that you can take a worse tour and a better tour, and when you apply 2-opt to the worst tour, you might get a better solution than when you apply 2-opt to the better tour. How many can see that? Yeah, it could happen. And there's lots and lots of other tricks you can do. Right? Okay, any other questions about 2-opt TSP, 1.5-opt TSP, post-processing steps, applying different flips and post-processing steps, you can combine them. And now let me ask you another question. What if you ran this heuristic that's no worse than twice optimal? Then you ran this heuristic that's no worse than 3.5 times optimal. Will this give you always a better answer than this? How many say yes? How many say no? All right, there's only 3 people voting, so let me ask again. Don't want to be presumptuous. All right, for the same point set, a fixed set of points, I run this heuristic. It's no worse than twice the optimal. I get a red tour. Then separately, for the same point set, I run this heuristic. That's guaranteed to give you a solution no worse than 3.5 times optimal. And I get a red tour here. I guess here I'm coloring it a green tour, but I get 2 tours. How many say this tour will be shorter than this tour? How many say that? How many say not necessarily? Good, now you're getting it. Why not? Yeah, these are just upper bounds. It doesn't mean that one is necessarily better or worse than the other in practice for a given point set. It's just an upper bound, right? I mean, if I say, this car, costs no more than $2,000, and this car costs no more than $1,000, it doesn't mean that this car is cheaper than that car. This car can cost only $1, even though I said it's not more than $2,000. I was still right. It's only $1. $1 is not more than $2,000. The other one, I say, doesn't cost more than $1,000, and the price is $900. So the other one was cheaper. It just didn't sound like that from the upper bounds. So what I'm getting at is, in practice, these upper bounds have almost no bearing on the solution quality on average. Right? So you run this many times or millions of times over random point sets, randomly uniformly selected from the unit square. You get solutions typically that are only a few % worse than optimal. Not twice optimal, not 100% worse, like the two bound here will suggest, but only a few %, 1.05 or 1.07 or whatever, 5%, 7%, at most 10%, not twice. Same thing for the other one. So if you run both of these heuristics together on the same point set and take the best of the 2 solutions, you'll do better on average than either one. How many can see that? Yeah. And which bound will you inherit? The better bound. So that's a good thing to do in general. You run different heuristics, some of which have bounds, other which don't have bounds. But now, the hybrid meta-heuristic will inherit the good bound of the best of them, and in practice will be better than any one of them separately. These heuristics can trade off expertise in terms of what they're good at and what they're bad at in terms of specific inputs. It's like division of labor, specialization of labor in society, right? You know, if you want to write a program, you can probably won't do it yourself because you're a computer scientist. But if you want to, you know, you need your appendix removed, don't do it yourself. You know what I'm getting at? So, you know, go to a specialist that does nothing but removing appendices every day long. And, you know, and of course, when that doctor needs to write a program, they're not going to do that yourself. They're going to come to you, the programmer or the computer scientist, and you'll do that for them. It's called division of labor. And I know it sounds obvious, but we didn't used to do that back in, you know, ancient times, you know, pre-biblical times. You know, everybody sort of had to do everything for themselves. You know, there was no organized societies way back. So life was a lot harsher then. But now, you know, we have specialization and division of labor. So same thing with these heuristics. Each heuristic might have instances of inputs for which it's good at, for which it's bad at, for which it's mediocre at. And other heuristics will have it all mixed around. But together, when you apply the same heuristic to the same, you know, you apply different heuristics to the same input and take the best of the end solutions, you might get something, and that average is better than any one of them separately. And the result can be very dramatic, actually. In other words, you can have two heuristics. One of them could be, on average, 20% worse than optimal. The other one, on average, could be 30% worse than optimal. And when you run them together and take the best of the two, together, they'll be no worse than 1% more than the optimal. That can happen. How many can see that? So it's not like you take the 20 and the 30 and average them together and come up with 25%. That's not how it works. Even though intuitively you might kind of think that that will be the answer. No, you know, it's much more dramatic than that potentially. Okay, any other questions about any of this? This meta-heuristics, and by the way, these meta-heuristics you can apply them anywhere. And not just about performance bounds, but about time bounds. So let's take an example from sorting, because everybody knows and loves sorting. So quicksort has great average case behavior. Asymptotically, quicksort runs how fast? N log n. Worst case, though, is bad. How fast is worst case for quicksort? N squared. Merge sort. What's the average? What's the worst case? Log n for both. Good. So how would you run quicksort in a way that still gives you the good average fast behavior of quicksort? That's why it's called quicksort, because it's fast. And yet, it'll never run worse than n log n time. Run them together. Now you're getting it. So run quicksort and merge sort together in the same input, using two processors or two threads, or in serial even, you know, just round robin. Well, you really want to run it together in this case. Let's run them in parallel on two processors or two threads. When one of them stops, you abort the other one. This will never take more than n log n time asymptotically. How many can see that? And the thing will be sorted. But the average case will be as fast as quicksort, modulo a small factor. What is that factor? You are paying a little bit. I mean, a little bit more space, because you're running them in parallel. Each one needs its own space. And in time? If it's true parallelism on two processors or two cores, you're not losing time. But if you're doing them on a single core with two threads, then it's time sharing the same processor with two threads, like time sharing and multitasking or, you know, threading or whatever, but only one core or one processor. There is a bit of price. How big is that price? About factor of 2, because you're running them together and you got to cycle between them, slicing your time between them round robin fashion. But the point is, you just modified quicksort to have worst case n log n. And you did it without dissecting it and going into the internals of the subroutine. You can do this with a library subroutine as a black box, not know or care how it's implemented, and still pull this trick by running another thing in parallel. And that thing is almost like a clock cutoff for that, and then the answer comes from another source, that other algorithm that you're running, merge sort or whatever. So these meta-heuristics are very powerful. And in real life, you can do this all over the place quite a lot. Venture capitalists do this in Silicon Valley. How many know what I'm talking about? Yeah. Right. They don't fund one company, they fund 10 companies or 20 companies. They don't know which one is the next Google, but they don't have to. They all start running in parallel. 19 will bankrupt themselves, like startups often do. But that one will become Facebook or Google or Amazon, and that pays off for all the other 19 that failed, plus a whole lot more. So that's what we can do here with heuristics, and it's arbitrary, and it's general, and it's a very good trick to remember. And in real life, you can do this in other places too, right? When you apply for jobs, you do this too. How many get it? You don't apply for one job and then wait to see what happens, and then apply for another job and wait to see what happens, or apply for graduate schools, right? You all did this. So you all already executed these meta-heuristics in your own personal lives. You're doing this all the time. It's called hedging your bet, right? You apply for 20 graduate schools or 20 jobs, and the fastest of them, 2, 3, 4 offers will roll in, and then others are slow or say, no, it doesn't matter because you already got your answer, you already got your job, and you're doing good. So, same thing with heuristics. Right? Any other questions? All of life is just a bunch of heuristics, right? Think about it. Yeah. More questions? Okay. So, but for here, the triangle equality has to hold.
We're also allowed to introduce edges in that situation, right? Normally, we're not allowed to introduce edges.
Well, so here, all the edges are implicitly there, even though they're not given to you, because it's a geometric version. Yeah. So I give you all the points, and the edges are implicit.
Yeah, infinite number of edges, and you play space.
It's not infinite, it's n choose 2. It's discrete. So if I give you n points, there's n choose 2 implicit edges across the n points, that's all. But you're right in the sense of graph. If the problem is in the form of a graph, it's TSP in a graph, the edges must be specified because a non-edge is not there. Well, let's put it that way. You can either think about it as an edge not being there, or you can think about it as an edge there with infinite cost. So if it's an edge that I didn't give you in the graph, it's still there, it just has infinite cost. So you never want to choose it. Right. So a few more facts. Non-deterministic polynomial transformations from NP-complete kind of transformations don't preserve approximability. We already mentioned that, but it's important enough to say it again. So just because you transform a problem to another problem, and that other problem is approximate, is well approximable, you're able to approximate it well with a good bound, doesn't mean that the original problem is approximable with a good bound, or that this transformation will get you a solution to the original with a good bound. The bounds don't survive the transformation, necessarily. They may or may not. Usually they don't. Now, there's a whole bunch of transformations that are approximability preserving transformations that are designed to preserve not just yeses to yeses and noes to noes, but near misses to near misses. Good approximations here to good approximations there. But most transformations are not like that as they stand. It's an extra feature of transformations that you have to think about and design into the transformation, and it's very hard to do, as you can imagine. I mean, it's hard enough to transform problems to other problems without worrying about approximability. When you have to worry about approximability while you're doing this, it's even harder. So I'm just saying. Now, some NP-complete problems can be approximated arbitrarily close to optimal, and some can't, even though they're all NP-complete. So don't get the impression that NP-completeness is some monolithic stamp of difficulty and nastiness and impossibility on a problem. there's hope even when things are NP-complete. So let me give you a few, examples of this good news. So far in this course, most of the news were bad, right? Like Rice's theorem. Almost any property is undecidable of, recognizable languages. That's really bad. That's bad news. The halting problem is undecidable. The undecidable problems, there's uncountable infinity of those, and only a countable infinity of decidable problems, because those correspond to Turing machines. So, Boolean formulas, Boolean functions, uncountable number of uncomputable ones, only a countable number of computable ones. So there's a lot of bad news. NP-completeness. Almost every interesting problem in real life is NP-complete. There's no polynomial time algorithm for it, likely. But here's some good news. Most NP-complete problems have easy, simple, fast heuristics that give you quick and dirty solutions, like we just saw for vertex cover and maximum cut, and now for TSP and many others. Right? Number two, many of them could be even come with a good approximation bound. Not, well, I don't know about many, but a substantial number, let's say. We just saw 3 different good bounds for 3 different NP-complete problems. Vertex cover and maximum cut, and now TSP. And many others have good bounds also for simple, quick, fast, quick and dirty solutions. Even ones that don't, the structure of the problem may be such that we can still solve large instances efficiently. So for example, SAT. We kept talking a lot about SAT and 3-SAT. And it turns out that SAT, even if you have large instances of thousands of variables, you can still solve that optimally in minutes or hours of CPU time, not days or months or millennia of CPU time. And there's entire conferences every year for SAT solvers, where they compete against each other who can solve the biggest random SAT instances, or even certain particular benchmark SAT instances. And these instances run into millions of variables, very large instances. And some SAT solvers can solve SAT instances of millions of variables and hundreds of millions of clauses in seconds or minutes. Let's say minutes. Seconds probably is a little, too much, but minutes, not hours or days. And if it's hours or days that they spend, they could probably solve instances with 100 million variables or a billion variables. Even though the problem is NP-complete, you can solve very large instances relatively quickly in practice in an exact manner, not approximation. So that's true too about a lot of problems. For TSP, even for particular real-life TSP instances, you can solve exact solutions for certain TSP instances that are thousands and thousands of points or sites large, right? Especially if they come from, cities on the map, because they're highly constrained instances. They're not just general arbitrary hard instances. Okay. And you can imagine how that would work, right? Let's say you find already a pretty good heuristic tour, and then you go out to find better tours, and you explore now the solution space kind of exponentially, brute force, looking at all possibilities, all permutations. But all permutations, you don't have to look down further than, because the permutation, as far as the first half of the tour will already be more expensive than the full tour that you already know exists from one of these heuristics. So you can cut the search right there, branch and bound, and look at other options and save yourself a lot of work. How many can see that? And you can every time you find a better tour, you can use that to bound the remaining of the search for other tours using other options, other permutations. And all of a sudden, you begin to exhaust the solution space faster and faster. And before you know it, you've covered most of it. And you only took a few hours of CPU time. A few hours, in quotes. That's a long time, but it's not millennia or the lifetime of the universe, like other NP-complete problems would require. So some NP-complete problems you can do this for. Others you can't. Others, no matter what you do, it'll take centuries of CPU time just to compute instances of size 20 or 30. But other NP-complete problems can solve instances of size millions or even hundreds of millions within reasonable practical times. So that's some of the good news. And in fact, for approximation of traveling salesman tours, Arora showed in mid-90s that you can get up to arbitrarily small times optimal. For any epsilon that you choose, you can do 1 plus epsilon times optimal. Of course, the price you pay is inversely proportional in epsilon in the exponent of the polynomial. So if you want no worse than, say, 1% more than optimal, 1.01 more than optimal, the exponent on the n in this polynomial will be 1 over 0.01. In other words, n to the 100. That's the price you pay for being that close to optimal in general. Now, of course, in practice, you probably get an optimal solution for many instances in real life way before you push epsilon that small. That can happen too. So it's all a matter of trade-off, time versus solution quality and how much you're saving. All right, so that's some of the, so general graph TSP cannot be approximated within any constant times optimal when metricity is out the window. So, this is not contradicting this. This is saying this is the metricity, triangle equality here holds, here it doesn't hold, and then you have no approximation. And that's provable that no approximation scheme exists at all for any constant times optimal, unless, of course, P is equal to NP, in which case not only approximation exists, but optimal solution exists in polynomial time. So, question.
Is there a complexity class for problems where there's approximation preserving maps exist for all the problems in that class?
I'm not sure if it's a general complexity class, because that would require a general theorem about what's approximable and what's not. But you can certainly define one, like you just did, in fact. You can sort of group together all problems for which good approximation exists within polynomial time, but you'll never know what that class exactly contains or doesn't contain, even though you just defined it.
Unless you prove that a certain type of a map always works for these problems.
Well, so it's not just about the maps. So, for example, if P is equal to NP, that class contains all of NP. If P is not equal to NP, that class contains P and maybe a few more, but not the rest, but not anything NP complete. You see? So you just defined a class that we're not sure what it is. And if you knew exactly what's in the class and what's not, one of the corollaries would be whether P is equal to NP.
But wouldn't it be like the completeness for this class? It would be such that like any two problems will have like some way to convert the near misses from one to the other.
Sure, but my point is, having said that, if P is equal to NP, what you just said will be true about all of NP.
Yeah.
Because it can also be solved exactly in polynomial time, so the conversion will just be, ignore the conversion, just solve it exactly over here, and that is a transformation.
But if the complexity class were to exist, the corollary would also be
well, so you have to think about exactly how you define it, but all I'm saying is it's easy to define a class. It's hard to kind of wrap your mind around exactly what you just defined. What exactly is in it or not in it. That may be not clear at all, or could be a major open problem, or it could be such a hard problem that P is equal to NP is just a simple corollary to knowing what's in the class and what isn't. So you have to be careful when you open these cans of worms. Okay, so graph isomorphisms. So graph isomorphism is one of those funky problems that is in the twilight zone between P and NP. We don't know that it's in P. We don't have a polynomial time algorithm for it, but we don't know that it's NP complete either. So graph isomorphism is basically an edge-preserving permutation of the vertices. So, for example, I give you this graph, and I give you that graph. Are they isomorphic? And yeah, they are, because you take this edge, this node, put it here, and move this around. This graph and that graph are the same graph. Basically, you could just rename the vertices, and the edges get preserved. So if you rename these 8 vertices into these 8 vertices, and they're color-coded. So this 5 becomes the G, this 1 becomes the A, and this 7 becomes the J, and so on, color-coded. This set of edges is exactly preserved here between the corresponding node renamings from the numbers to the letters. How many get this with isomorphism? Okay, it basically doesn't change your graph, just renames all the vertices. Turns out it's a very hard problem. We don't know how to solve it in polynomial time, as simple as that problem sounds. But we can exploit the fact that it seems to be hard to do other things. So that problem, those examples might be easy, but are these two graphs isomorphic? How many say yes? How many say no? You see, it's hard to say, even though it's only 10 nodes. But what if I showed you more graphs, these three graphs? Are there any two isomorphic graphs on this slide? Any two of the five are isomorphic? How many say yes? Some are isomorphic. How many say no? Again, it's hard to say. But let me show you an animation. How many say these two first graphs are isomorphic now? Yeah, but because I showed you the animation of how one morphs to the other, isomorphs to the other, right? Isomorphic. See, it continuously changes from this guy to this guy. But without showing you this animation, it's hard to say. So once I show you the isomorphism, it's easy to verify that it is an isomorphism. Now it turns out that not just these three graphs are isomorphic here, all five are isomorphic to each other. Except it's a little harder to see the other isomorphisms without me actually giving them to you. So it's a tough problem, and that's just 10 nodes, right? What if I gave you 100 nodes or 1,000 nodes, 10,000 nodes? You can see how it would be hopeless very quickly. So this gives the idea of zero-knowledge proofs. You can prove an isomorphism without actually giving you the isomorphism. So here I gave you the isomorphism. I showed you which nodes transform into which other nodes. Okay? So these two nodes became these two nodes here. But what if I just wanted to show you that these two are isomorphic without actually giving you the isomorphism? How could I convince you of that? So this is a major technique in crypto. Proving an isomorphism exists without actually giving the isomorphism, and moreover, without disclosing anything about the isomorphism. Not even one bit about the isomorphism is disclosed. So we're about to show how that happens. So this has a lot of applications in friend and foe systems and transactions, financial transactions, and lots of things. So here's the protocol. The protocol is just a fancy name to say algorithm. Everything is an algorithm. So everybody knows the isomorphism between two large graphs. They're published on the web, and excuse me, they don't know the isomorphism. They know the two large graphs, but the isomorphism is only known to somebody as a secret, and they need to convince somebody else that they know the secret, but without disclosing that secret. Okay. So friend and foe identification. You have a military plane coming into a military base, flying at twice the speed of sound. The military base doesn't know if it's a friend or foe. It could be an enemy or a friend, and it needs to determine very quickly which is which, because it has to take two very different actions based on whether it's a friend and foe. If it's a friend, it needs to come in, let it come in and land safely, and maybe even provide protection. If it's a foe, if it's an enemy plane or a drone or a bomber, intending to do you harm, you cannot let it come in, and you have to shoot it down as quickly as you can. And either error, the false positive or the false negative, are very, very expensive, right? If you let in a foe and it bombs your base and possibly kills you, that's a very bad day for you. If you mistake it the other way and mistake a friend for an enemy and shoot it down out of the sky, even though it wasn't an enemy but a friend, that's another bad day for you. It could be court-martialed, or definitely your career will suffer. And not to mention whoever's on the plane will die. So you can't make a false positive, and if you can't make a false negative error, you want to avoid both very, very dearly and seriously. So typical war scenarios in the old days, World War I, World War II, plane would fly in, or this is not just about planes. Enemies advance, a tank comes in, a vehicle, a soldier on soldier kind of encounter. They would have some password, and they'd say, blue sky over the air, and then the people on the ground will say, okay, that's the right password, let them pass. But the enemy can hear this password being transmitted over the air and next time spoof it and transmit that themselves, whether it's encrypted or not encrypted. They can still transmit a spoofed recorded password, and then that could fool the ground station next time, and some havoc could occur, right? An enemy can now slip by transmitting some false password that they just heard transmitted yesterday or an hour ago or a minute ago. So you don't want to transmit anything over the air. You don't want any passwords to be transmitted over the air, yet you want to convince the ground station that you're a friend and not a foe. All right, so how do you do that? It sounds like an impossible task, right? How can you convince somebody that you know a secret password without actually disclosing to them the secret password in any way whatsoever, not even encrypted? So it sounds impossible, but you can actually do this with very high likelihood of success. So the password here will be the isomorphism between these two graphs. The red isomorphism here will be the password. These are two large graphs, 1,000 nodes, 10,000 nodes, two very large graphs for which nobody knows the isomorphism except this plane. And by this plane, I mean the chip on the plane. It's not even the pilot that needs to type stuff in. Flying at Mach 2 pilots don't, do that. But the chip on the plane knows the isomorphism. That's the only place in the universe where the isomorphism exists. And it's easy to make that happen, to enforce that restriction, because when you manufacture the chip for the plane, you create two large graphs. One is an isomorph of the other, and you etch the isomorphism on the EEPROM or whatever of this chipset on the plane, and you erase that knowledge from anywhere else. You don't store that knowledge. You just generate two large random graphs. You record the graphs. In fact, you publish them to the web. These graphs are world publishable. They're world knowable. Everybody can see the two graphs, but the isomorphism only exists aboard the plane. It's easy to do. By the way, how do you create an isomorphism of a large graph? Relatively easily. You just randomize the nodes, and you got it. So it's easy to do. Discovering the isomorphism, if you don't know it, that's the hard part. That we're not sure how to do efficiently. We know how to do it brute force. How do you find an isomorphism if two graphs are isomorphic? If two graphs are isomorphic, how do you determine that brute force if time wasn't an issue? If you had all the cycles in the universe.
Assign every node in the second graph.
Yeah, look at all permutations, and then if one of them works, check if any one of them works with respect to the edge preservation. And then you'll know if they're isomorphic or not. But of course, it's an exponential number of permutations, an n factorial permutations. And n factorial grows like n to the n. It's even worse than 2 to the n. Okay, so the only knowledge of the isomorphism in the entire universe is aboard this plane. And when you manufacture these planes or tanks or whatever vehicles, ships, you can create a pair of isomorphs for each one, publish them on the web, and the isomorphism is only etched onto the chips of that particular platform and nowhere else. Okay, so now the plane has to convince this missile ground station that it knows the isomorphism between two large graphs that everybody is aware of, but it cannot transmit the isomorphism to the ground. Because if it did, the enemy can eavesdrop on it and next time transmit that same isomorphism and fool the ground station next time around. That's not going to be good. So the isomorphism must remain secret and not even be transmitted, even in encrypted form. All right, so here's how the protocol works. The plane creates an isomorph of one of the two graphs, G. And that's the green isomorphism here. And then the ground station asks to see one of the two isomorphisms, either the red one, or either the green one or the blue one. Notice that once you have the red isomorphism and you create another isomorphism in green, the blue isomorphism implicitly is the composition of the two. Because a permutation of a permutation is another permutation. Right? But the ground station gets to choose, once you broadcast this graph G to the world, including the ground station, you can do it unencrypted. Right? No encryption is used here. This ground station, which is also called a verify, asks to see either the green isomorphism or the blue isomorphism, not both. And you're not going to give them both, because if you give them both, they'll automatically know the red by composing the two. So you're never going to give them both. But you can give them either the green or the blue. Now, if the green was really if this graph G was really an isomorph of both of these, you'll have no trouble supplying either the green one or the blue one. But if G wasn't an isomorph of one of these, or if it was an isomorph of one and you didn't know the other isomorphism in red, you'll never be able to supply the missing isomorphism, the third isomorphism. How many understand that? Without a lot of computation of your own, of exponential amount of computation potentially. So the verifier has to see either the green or the red, or either the green or the blue isomorphism, and then you broadcast, based on the verifier's request, either the green or the blue, whichever one they ask to see. So if you were lying and you didn't know the red isomorphism because you were an imposter, a spoofer, you'll be able to supply the green but not the blue, or the blue but not the green. So the chance of the verifier catching you on the lie, if you're lying and you're an imposter, a spoofer, the chances that you'll fail this test is what, roughly? About a half, right? Maybe you luck out and only know the green, and the guy will ask you for the green, and you'll be lucky and be able to supply the green. But if he asks you for the blue, you'll be in trouble because you don't know the red because you're an imposter. And if you knew the green and the blue, you know the red because you can compose them same as anybody else. So 50-50 chance they'll catch you on a lie. Now 50-50 chance is not great odds for either dying or being court-martialed that day, which is the false negative and the false positive outcomes, right? Either killing a friend or be destroyed by a foe if you make a mistake, either direction. So how would you improve the odds? The odds are not in your favor right now. Repeat this whole protocol many times. And by many, we don't need even that many times, right? You can repeat it, say, k times for, I don't know, if you repeat it 30 times, let's say, what are the odds that you're a spoofer or a cheater and still be able to pass 30 times through this protocol without getting caught? 1 over 2 to the 30, which is 1 in a billion. 1 in a billion is pretty good odds, to either, to not make a mistake. And if you don't like a billion, do it 40 times, then it'll be 1 in a trillion, roughly. How many understand that? Any questions about that? Yeah.
Does the airplane or whatever have to make sure that, they don't send a G that's equivalent to G2?
Yeah. So you need to, from a practical perspective, make sure, first of all, that its two graphs are large. Not only that, make sure that they don't have a lot of different degrees in the graph. If one graph is isomorphic to another, and you have only one node of degree 17 in both graphs, what can you tell me about that node in both graphs of degree 17? Those are equivalent in any isomorphism, never mind that particular one. So make sure that the lot of degrees are all the same. Make sure there's a lot of degrees are all 500. And that's not hard to do. You can create very large graphs with a lot of degrees repeated many times. And make sure the graphs are large. You don't do this with graphs of size 50 nodes or 20 nodes or 30. You do it with graphs of size 10,000 nodes. But 10,000 node graph is not very much in terms of data transmitted. It's just 10,000 nodes, and then the edges are pairs of nodes, and there's probably a few hundred thousand. So only maybe a megabyte or something, or even less. Compressed, it'll be a lot less than a megabyte. You can transmit these graphs very quickly, in milliseconds, not even seconds. So doing that is very quick, actually. And checking isomorphisms, again, is very quick and so on. So there's nothing computationally difficult in this protocol, but with very high probability, the verifier on the ground will be able to check and convince themselves that you possess the secret, and secret being the isomorphism, without you disclosing anything about that isomorphism whatsoever. Also, you want to make sure that through successive iterations, you don't create the same graph multiple times. So if this G that you generate randomly, that's an isomorph of G1, you don't want to create the same G the next iteration. Why not? What if you use the same G transmitted down 2 different times among the 30 times that you play this protocol with the verifier?
A person listening in could use it, isomorphisms gotten from 2 different instances?
Yeah, not even the person listening. The verifier, a person listening in, but even the verifier itself can notice that it got the same graph again from 17 rounds ago, and this time it won't ask for the green like it did last time. It'll ask for the blue. And once you supply the blue, it'll compose the two, and now he'll know the red, and so will anybody who eavesdrops on this communication. So you don't want to supply the same graph twice. But that's easy to do also. How do you ensure that you don't supply the same graph twice? Well, you just remember all the graphs that you supplied, make sure it ain't the same. Or you can just generate them randomly, and the chances are that you'll generate the same 10,000 node random graph twice in this lifetime of this universe are almost zero. How many get that? Yeah. So you don't even have to remember them all. You just that's even less of a probability that a cheater will not be caught, actually. The same graph will be generated twice. And there's a few other technical issues like that, but this works pretty nicely. Any questions about that? Yeah.
In practice, is graph isomorphism used a lot for PCPs, or is it mostly like discrete log?
You can use any NP-complete problem. Actually, you can do better than that. You can use any problem in PSPACE. But any NP-complete problem you can do the same for. And graph isomorphism is as good a thing as any because it's easy to compute, it's easy to create isomorphs, it's easy to check permutations against one another if they're the same or not. So this works pretty nice. So in some sense, this is approximating a proof. In other words, this is sort of an industrial grade proof. Right? It's like industrial grade diamonds. They're not quite as perfect as, jewelry diamonds, but they're pretty good. They have all the right properties. So this protocol is a proof, industrial grade proof, an almost proof, a practical proof of some fact without disclosing the fact whatsoever. And the way to prove that no knowledge leaks through this, it's not obvious that it's hard to tell what the isomorphism is, but it's not obvious that it's zero knowledge. The reason it's called zero knowledge is because not even a single bit leaks through this information, theoretically speaking. And the way to prove that is the verifier, or anybody that listens, doesn't get any information more than they already know or can easily compute on their own. Because all you're doing is sending a permutation of one of the graphs. If they want a permutation of one of the graphs, they can generate on their own. They don't need you for that. They also have a random number generator or a pseudo-random number generator, and they can do that just as well. So they're not learning anything by seeing a permutation of one of the two graphs. Remember, those two graphs are public knowledge. Anybody in the world can see them. They're published on the web, in fact. What's a deep secret is this isomorphism between them in red, not the graphs themselves. Yeah.
So how does PSPACE know which graph it is going to ask for the proof?
So you don't know which graph it's going to ask for, which isomorphism, the green or the blue, it's going to ask for. But you have to be ready to supply either one.
No, my question is, so the plane sends G to the base, and base needs to say, either you please verify that the isomorphism between G1 and G2.
Well, so it asks to see either the green isomorphism or the blue isomorphism. The verifier verifies it on their own. So you're not verifying it for them. You just send them the isomorphisms and say, here's the permutation. And then they look at the permutation and check that this
is done by base.
The check gets done by the best. That's why it's called the verifier. So this guy is the verifier down here. It verifies that the isomorphism that you sent it is a correct one. That's important. It's doing the checking. It's not taking your word for it. But checking an isomorphism once you hand it to you is easy. Right? You just run the graph through the permutation and see if it's equal to the other graph. Because I'm giving you the permutation. Which one? The one that you asked for, either the green or the blue. I'll never give you both, right? Because if I give you both, you can compose them and infer the red very quickly.
But how does base know this is a permutation of G1 or G2, right?
So the plane knows the red permutation. So because G is an isomorph of one of them, it's also an isomorph of the other one.
But base doesn't know.
The base doesn't know.
So what base gap is just G and
Yeah. So I have two graphs, and one of the graphs, I give you a graph that's isomorphic to both. And you know it's isomorphic to both because you know that I know that the two are isomorphic, and I know the isomorphism. You don't know the isomorphism, but you know that I know the isomorphism.
But I don't know which one is G1, which one is G2, what they are. I don't know.
No, you do know. You do know because G1 and G2 are published on the web.
And they are paired together?
They are paired together. Yes. Yeah. And not only that, they are paired together for this plane. But that's a side fact. But they are paired together. So you know the pair G1 and G2, they're published literally on the web for the entire world to see, unencrypted. That's the beauty of it. It's completely transparent to everybody, including your enemies, not just your friends. So the only way you can supply consistently either the green or the blue whenever you're challenged to do so is if you knew the red. Because if you didn't know the red, maybe you're lucky and can supply the green if G was an isomorph of G1, or you could supply the blue. But you'll never be able to supply either one consistently, always correctly, whenever you're challenged, every single time. Because if you could do that, that means you do know the red, simply by composing the green and the blue. So I'm going to catch you on a lie 50-50 for every round, but if you can keep passing these rounds, you're less and less of a liar and more of a truth teller, really in possession of the red isomorphism. So I'll give you an example from real life, right? So we went through this whole course, 3 months, and I asked you to study a lot of stuff, read a lot of stuff, do a lot of problems, solve, and I'm not sure if you did this or not. I hope you did. So I'm going to go through a protocol, next week with you. I'm going to pick a question, throw it at you, and see if you know the answer. And if you do, okay, I'll do it again. And if you know that answer, I'll do it a third time and a fourth time, maybe 6 or 7 times. That won't tell me if you studied all 500 things that I expected you to learn in this course. And there's literally hundreds of things. I actually made a list, it's in my slides. Hundreds of theorems, facts, definitions, transformations, algorithms, clever MacGyver tricks, and all sorts of things. I don't know if you studied all 500 things, but after I throw about 6 or 7 things at you, and you can reply correctly for each one, I'll be more and more convinced that you know the other 497 things, or however many there are. What is that protocol called? It's called a final exam. Okay? It's exactly what it is. And it works exactly for this reason. It's a sampling process. Right? I sample your knowledge a few times, and from that I infer that you know a whole lot more. And I don't have to test you on 500 different things, which was the entire contents of this course. Luckily for you, and luckily for the TAs that will have to grade all that, right? So it works. So that's a pretty good protocol. That's why we have exams. That's why exams work, right? So this is kind of a sampling of the knowledge of the prover a bunch of times until the verifier is highly confident that the prover has complete knowledge of the isomorphism. The verifier will never be completely sure. Just like I will never be completely sure if you studied for this course all 500 things that I wanted you to, just by asking you 7 questions. Maybe you're just very lucky, and that's the only 7 questions that you studied and I happen to ask you, and you get them all perfect, and the other 493 things you never bothered to look at. But for that to be true, you have to be very, very, very lucky, not just a little bit lucky. Right? It's almost, almost infinitesimally small probability that will happen, right? And that's definitely not a chance you want to take. So that's exactly what happens in real life, right? Now this codifies it algorithmically as a protocol, and now you could pull these tricks with lots of other NP-complete problems, right? So you can do this with colorability, right? So you can do this with colorability. I'll just show you the whole thing, right? Let's say you know the coloring of a graph. So you know the coloring of a graph, but you don't want to give the coloring to the adversary that's challenging you, or potentially a friend that's challenging you, so whoever. You want to prove that you know the coloring, but not actually give it away. So you create an isomorph of that graph, and then the enemy, or the verifier, asks to see either the isomorphism or the coloring of the isomorph. One of the two. Either the isomorphism or the coloring of the isomorph. Now, if you can consistently either provide the isomorphism or the coloring of the isomorph, you must know both. And if you know both, the isomorphism and the coloring of the isomorph, you know the coloring of the original. And the enemy is not getting any information because they can create as many isomorphs as they want. Right? So by giving them an isomorph, you're not really saving them any computation that they can't already do on their own. Right? You're not making their life any easier. How many understand that example? So you can keep going like this and embed any NP problem into this. So in fact, again, you need a good random number generator because you don't want to produce the same, graph twice, or, but it doesn't have to be that great a random number generator, just a decent one, a good one. Never use the same graph twice. Use graphs which are large and complex, don't have different degrees. You should have a lot of the same degree repeated, and so on. And then you won't make the false positive and the false negative errors, which are both very severe. So there's lots of applications of this in friend of foe identification, also in crypto, of course, in business transactions. You have a credit card. Today's credit cards have chips in them. How many have chips in your credit cards? Almost everybody does now. And the chip in your credit card is playing the zero knowledge proof protocol with the register of the vendor. So the chip on your card doesn't disclose your credit card number. All it does is playing this kind of zero knowledge protocol where it convinces the cash register of the vendor that it's a valid credit card number, it's in your name, it has enough balance to cover the transaction, and so on. It's not stolen. And after a few iterations, after a few rounds, 20, 30 rounds, this happens in milliseconds, it doesn't take very long, the cash register, i.e. the vendor, is convinced that you are a valid, honest customer, and then the transaction is locked in and everybody's happy, and they still don't have your credit card number, so they can't spoof it and sell it to a third party on the dark web or whatever people do with stolen credit card numbers these days. So this actually happens in financial transactions. Question?
Is the reason why PSPACE problems are sufficient because IP equals PSPACE?
Yeah, so a few more facts. So by the way, you can do this with satisfiability. One way to get it done is when arbitrary problems in NP, you can push them through the NP-completeness proof. Reduce a problem in NP to satisfiability, and then use satisfiability into colorability, and then use this protocol that we saw for colorability. So by compounding these transformations, you can basically handle any NP-complete problem. But more than that, you can handle any problem in IP, which is equal to PSPACE, like you said. So first, the prover has an unbounded power and can be malicious. You don't even have to put restrictions on the prover. The prover could be nefarious. It can be malicious, right? And he trying to convince. So even if the prover has unbounded computation power, even if it compute all of NP in constant time, never mind polynomial time, they still can't fool you under this protocol. So this protocol is so powerful that as long as the verifier is honest, and the verifier even if the verifier is honest and has limited power, they can still not be fooled, even if the prover has unbounded power and is actually highly malicious. If the statement is true, what you're trying to prove, an honest verifier will be convinced with very high probability. Okay? And if a statement is false, even an omnipotent, malicious prover cannot convince an honest verifier that the statement is true. So it's complete and it's sound. With very high probability, this will succeed in its goal of convincing a verifier that you actually are in possession of this piece of information that only you can be in possession of, thereby proving your identity or intent. So the induced complexity class also depends on the verifier's abilities and computational resources. So for a deterministic polynomial time verifier, the class is NP. But for a probabilistic polynomial time verifier, if the verifier has access to random bits themselves, through randomness, the induced class is called IP, interactive proofs. And in 1992, Adi Shamir, the S in RSA, that Adi Shamir, proved that IP is equal to PSPACE. In other words, you can do this for every problem in PSPACE, as long as the verifier has probabilistic capability as well. But if the verifier is only polynomial time deterministic, the class is still all of NP, which is a lot. These protocols have very practical, real life potential, and they're getting used already quite a bit. And of course, it's also a cryptographic protocol that can be used in other cryptographic protocols as a subroutine. But that's the basic idea, and there's entire conferences on it these days. But before the late 80s, we didn't know any of this, could happen. We didn't know that you can pull this kind of stunt. We thought that in order to convince some fact or theorem or truth or secret of, to somebody, you have to disclose that. If you wanted to convince somebody a secret password, you have to give them the password, and then they can verify it. Or maybe you can give it to them in encrypted form, and then they can verify that. But we had no idea that you don't have to give them the password at all whatsoever, not even in encrypted form. That we didn't even know it was possible until we learned about zero-knowledge proofs in the 1980s, and now the rest is history. Any more questions about this? This could also come in, handy in political situations and diplomatic situations, delicate business negotiations and so on. When you want to convince somebody of some fact, but you can't disclose the fact because that will just give away too much information. But you still need to convince them that that fact is true. So there's lots of scenarios where you can apply this. It's going to come in legal situations. Let's say you have you want to prove an alibi of some kind, that you're not guilty of a crime because you were somewhere else, but you can't disclose where you were because it's highly sensitive and maybe it's private information. But so you're in a bind. You want to convince the jury or the judge or the court that you were not there to commit the crime, but you don't want to say where you actually were, just that you weren't there. Now, this can enable you to do that, maybe, if you play it right, yeah.
So would Diffie-Hellman just be an interactive group then, because you're just kind of like one side is locking part of it, and then the other side is putting another lock?
You can think of, in an abstract way, a lot of protocols are like this, have this kind of flavor. So one of the issues here is interactivity. It's interactive. It's not just I do something and you do something and we're done. No, we keep iterating. You do something, I do something, then you do something, then I do something, and we keep going around and around and around until we're both satisfied. So it's not a one-shot thing. It's iterative. So a lot of things in crypto are like that. A lot of things in real life are like that. We already mentioned final exam in a course. We have quizzes, we have homeworks. So the whole course is one big interactive proof that you're learning what you're supposed to learn by doing the assignments one after the other, and even attendance. That's, of course, it's not completely zero knowledge because I see you, I know who you are. But theoretically, you could be watching my lectures on the web and giving proof that you're doing that without disclosing exactly how you watched it and where you watched it and what time you watched it and whatever. You can kind of stretch it out to a lot of different scenarios. It depends on how widely you define these kind of interactions, but there's a lot of kind of interactive proofs, techniques or protocols or real life situations where you iterate with somebody as you learn more and more back and forth, and while keeping some things private. There's even protocols, cryptographic protocols, something called mental poker. You can play poker over the phone without the ability to cheat. How many heard of that? Mental poker. So you could use public crypto system to encode all the cards and simulate a deck of cards over the phone just by passing information back and forth, and you don't even know your adversary who's on the other side of the phone, but both of you know that neither one of you is cheating. There's ways to think about how you would do that. This was known already in the late 70s, how to play mental poker or gambling in general. Now, that's not to say that when you sign on to a website, to a poker website or a gambling website, you're protected. You're probably not, actually. So, there's probably scammers on the other side. Chances are. But technically, that doesn't have to be. If you had mental poker kind of protocol that you're playing with a website and they responded in kind, neither one of you would be cheating. And the other one would know that you're not, with very high probability. Unless you break the crypto system, whatever that is. So there's a lot of applications of these kind of things. Okay, anything else for now? Yeah.
Convert to a non-interactive, like for this setting, you are supposed to the parties to be online.
Yeah. So you're asking if you could do this without the parties interacting at all?
Yeah.
Probably, you know, I don't think so. Not is there a way to do that?
Non-interactive zero-knowledge arguments.
Okay.
So in cryptography, they use a lot of non-interactive zero-knowledge.
Does it have the same properties?
Yeah, it's zero-knowledge proof. It's the same soundness and completeness, but it's non-interactive. There's also another version of this called SNARKs.
Mm-hmm.
Succinct non-interactive zero-knowledge arguments.
Oh, okay. Well, there you go. So he knows more about crypto than I do. So, yeah. What else? All right. So let's take a short break, 15 minutes, and then continue.